All right. Hi, everyone. Welcome back. Today our speaker is Praneeth Vepakomma. He's an assistant professor right now at the Mohammed bin Zayed University of Artificial Intelligence. And he's also an visiting assistant professor at MIT, where actually he got his PhD. He also kind of like spent a lot of time in industry, so he's pretty much done everything you can do in life. So today he's going to, I mean, his research in general is like in trustworthy AI, responsible machine learning, collaborative data science. And today he's going to tell us about his work on postdoc privacy guarantees for neural network queries. So, Praneeth, it's all, yeah.
I think Ajuba, this is great. I've been following your workshop for a while, so I'm glad I'm speaking here. All right, let's get started. Okay, so the focus of the talk is mostly around neural network queries, right, for training and inference. And of course, there's been tremendous work, ongoing work at the intersection of privacy-preserving machine learning and also independently at times and different paradigms for distributed machine learning, like federated learning and so forth. If you look at some of the broader privacy mechanism landscape in ML, there's been a lot of work on gradient perturbation, so DP-SGD style methods, and there's DPFDRL. There's been some work on label perturbation for label privacy in conjunction with DP-SGD or DPFDRL. There's been some work, especially for convex or like Lipschitz smooth style functions for objective function perturbation and trying to get some amplification for privacy based on the contractive nature of your optimization of data and so on and so forth. What has been a bit understudied and also for logically more valid reasons is the question of privacy for inference. So privacy for inference or privacy during inference with respect to your inference data itself. This by itself leads to some sort of an impossibility result unless there's some sort of a relaxation done on this problem. Okay, so at the same time, another aspect that has been a bit understudied is when I say privacy, I'm talking of some notion of formal privacy or at least pseudo-formal privacy instead of completely informal privacy or something of that sort. Same thing in terms of privacy for activation. So most perturbations we are seeing has so far generally been for releasing weights of the neural network with privacy. So weights as some sort of a statistic of the neural network as opposed to activations, which is again a bit tricky because activations are these one-to-one functions. They're almost infinite possible inputs, and then you have this one-to-one corresponding activations as opposed to a weight matrix or like a weight tensor, which is more of a statistic in some sense. So trying to understand, trying to portray a bit of the system's interactions before we get into the algorithmic nature of the mechanisms. So I'm focusing here in this talk, at least the first half of the talk, on the setting of private collaborative inference, which refers to the inference process being distributed across, say, a client-server setting. So a good cartoon example could be some sort of a voice assistant or some sort of an assistant that's a client, an edge device that takes in the raw data during inference. And the model with which you're supposed to infer is kind of distributed between the client and the server. So basically, the voice assistant has some model that converts your data into some sort of an embedding. And I'm using the word embedding a bit loosely, so some sort of a representation of your data. And that representation is certainly sensitive. Your data is sensitive as well, if nothing was done to it. And that sensitive representation is sent to the server, where the server continues some of the processing with its larger models that it has on device. It's like a machine learning as a service that's being split between a client and server. So this is private collaborative inference. And of course, comes the question of how do we privatize this kind of a communication or interaction? And like I said, this is a bit distinct from the setting of say, private model training, where you're dealing with weights as opposed to activations. Here it's about the client downloading the model once you release it with privacy. Here it's about the inference being distributed. The tricky nature comes from the third row, which is you're looking at sample at a time, which makes it, is this even like well-defined formally? Okay. And the title of the talk was referring to post hoc. So that basically refers to the setting that the embedding model could be some sort of a informally private or like a heuristic model that is useful for learning, but there's some heuristic in terms of some sort of leakage reduction. And this is and if someone comes up with a heuristic model that is very useful, but no one knows how to put in privacy on top of this informal pipeline, that's the question of post hoc privacy. You don't want to redo the whole process and come with a private model, but you want to do some additional processing and somehow infuse privacy post hoc. All right. So that's the question, right? So how can an informally private pipeline or model be made to provide formal privacy guarantees? Okay, and this is based on our NeurIPS work. Okay, so this is traditional machine learning as a service, top left. Top right is machine learning as a service with some sort of an informal model where you have some sort of an obfuscator which has no formal privacy guarantees. But it is some sort of an adversarially learned representation that is maybe trying to prevent some sort of an attack. So there's no worst case nature of prevention that this is dealing with here. And the post hoc framework tries to do some more additional processing that makes the whole pipeline formally private before this communication is stopped. Okay, and when I say informal privacy, that word itself sounds not very formal. So what am I referring to? So I can just give you some examples because there's no definition of what an informal privacy is. For example, on the right, you see these faces of the women from a CVPR paper where they introduce some sort of a informal pipeline which they test and benchmark against different reconstruction attacks. So they share some sort of a representation, like we saw in the previous setting, of these images, and they just test it empirically, purely empirically against some benchmark or reconstruction attacks. Again, empirical attacks. And there are many, and then they somehow, try to present some sort of visualizations or quantify or some qualitative analysis of how this leakage is being reduced across different blocks of the neural network using their method of training and so on and so forth. There are many such papers mostly in applied machine learning style conferences or applied vision or like NLP conferences that talk of methods like pruning your neural network channels so that it prevents some leakage or trying to decorrelate based on some notion of divergence that you care about, trying to disentangle, trying to include some shuffling. So since it's informal, we don't know if this is privacy by obscurity, which is not private, or if it is formally private. So that's the problem. So how can these models be made formally privatized in a post hoc manner during inference? Okay, since we're talking about privacy, I need to pay due respect to what kind of privacy I'm broadly referring to. So a starting point for this is, of course, differential privacy, and there's the definition of differential privacy. The one on screen is a definition for what's known as pure differential privacy. So a mechanism is epsilon pure differentially private if the PDF of the output of your mechanism doesn't vary up to an e power epsilon in the supremum or the uniform case. In the worst case, when that mechanism is applied on two databases that are neighboring, where the notion of neighboring traditionally has been Hamming, but there's been other notions of it under metric differential privacy where it changed the metric. Okay, and traditionally there's just a definition or standard of privacy, and there are mechanisms or protocols that come along that came along in the landscape of what happened and this is going on for different sorts of queries, and typically there's some sort of a randomization, well-crafted randomization or a randomized data structure or noise addition that is included in the pipeline in order to reach and prove these kind of guarantees for any given query, corresponding query. There's been some equivalences of what the definition of differential privacy means, or like some sort of equivalent base of understanding differential privacy. I've listed a few in here. One is based on the notion of what is known as a privacy loss random variable, which is the instantiation of how this loss, which is, you've seen the definition in the previous slides, but if you just rearrange it and look at the instantiation of how the loss changes within the e power epsilon mark, that's known as the because the epsilon is the worst case thing, the epsilon is the worst case, but maybe you have a mechanism where you are being more conservative in reporting your epsilon, which is still fairly private, which is truly private, but from an epsilon sense, but maybe it's performing in a not so conservative way. Maybe it's more private than you think it is, and so on and so forth. So in order to understand this behavior, people have been looking at privacy loss random variables, and then the distribution of this privacy loss random variable as well has been useful in being able to compose queries without losing your privacy budget. Because when you do a composition of queries, you start losing your budget. But if you budget in a too conservative way, then you lose your privacy budget quickly as your epsilon blows up soon. But if you compose it in not so conservative way while still being correct, you preserve your privacy budget. So there's been a lot of privacy definitions, equivalent definitions like RENU DP and zero constant DP and so forth that are based on this room for improvement while budgeting. This is a plot that we made in our actually literally our collab notebook, where we show that you can. So the benefit of looking at privacy loss distribution as follows. If you had a composition of queries and you want to know what the privacy loss distribution is after the composition, all you need to do, or one way to do it, is you convolve the individual privacy loss distributions of the two queries that you're composing, and then you end up getting the privacy loss distribution as if you composed and checked what it is. And this is somewhat more wieldy to implement computationally, because this convolution doesn't have to be done purely analytically. You can implement this by uniformly sampling from individual privacy loss distributions and adding those samples. That's equivalent to the convolution operation. Or you could have done this in the Fourier regime with the pointwise multiplication, so on and so forth. There are some equivalences with respect to information theoretic divergence called hockey stick divergence. So epsilon delta dp is equivalent to this divergence being within this bound. And the divergence itself is parameterized by the epsilon. There's been equivalences with respect to what hypothesis testing is in the setup where you're trying to model an attacker who's trying to figure out if a record is trying to do a membership inference attack, basically. So there's many equivalences. There's some well-known equivalences. The ones that I've shown here are mostly well-known. There's some slightly less studied ones, such as the Lipschitz differential privacy, which we bank on a little bit. So the point of this slide was to show that DP has different equivalent notions of understanding it, and there's one kind that we are going to be exploiting more. Okay. Now that you've seen some definitions of differential privacy, classically, the ones that deal with additive noise style mechanisms in order to lead to differential privacy guarantees are based on calibrating your noise to of course your privacy level, but also the variance of your noise to what is known as the global sensitivity of a query. This is purely a property of your query, so it's query dependent, not necessarily data set dependent. So this is basically measuring what is the maximum change within a norm of the output of your queries when you apply it on neighboring data set, on all possible neighboring data sets within the domain in which the neighboring data sets can lie.
Can I answer just a super quick clarification? Just I'm starting the slide quickly. When you say local sensitivity and global sensitivity, you're talking about local sensitivity in the central model.
Yeah, yes, that's right. This is in the
Just want to make sure.
Correct. Because yes, and to clarify for the audience now and later, we are dealing with this capital D in here, where you have like a data set, as opposed to adding privacy at every single record level, for example. That's another way of thinking about it. Yes, and this is kind of a segue into the post-hoc privacy framework while introducing DP. At the same time, one could do if one doesn't have a good way to figure out what the global sensitivity of a query is, people started thinking about other notions of sensitivity, and there's been one notion called the local sensitivity, which doesn't necessarily lead to a privacy guarantee, but it's a thought. So the thought there is it's a data dependent or like a point dependent, input dependent notion of how sensitive your query is, which is again measuring how much your query would change around a given point within up to some norm. But this doesn't guarantee DP. And then there's been other sensitivities, such as smooth sensitivity. There's been one on down sensitivity and so on and so forth, when you don't know what the global sensitivity is. Okay, so in the scenario where you don't know what the sensitivity is, there was this kind of seminal paper among many other important DP papers by the DP community called the proposed test release mechanism, which deals with this scenario where the one could propose a local sensitivity or their estimate of local sensitivity of the query that they're trying to privatize. And of course, since they know that the local sensitivity may or may not be enough of a sensitivity to calibrate your noise in order to guarantee privacy, there needs to be some notion of testing or some sort of a gate that says, okay, what you proposed is good enough so that if you add noise calibrated to that sensitivity, you would get privacy. Or you need the gate to say, oh, no, this is not good, so that you use this oracle somehow, again, try to repropose your sensitivity with which you want to calibrate your noise. Okay, so so this is the structure of the PTR, the steps of the PTR framework. So you propose, and then there is a step where you try to find an instance of the data at which at which the local sensitivity bound does not hold. So the proposed bound does not hold. You want to find a breaking point or like an instance, and then and the framework also tries to measure how far that instance is. And once you do that, they since that is figuring out how far it is also a private function of your data, of your sensitive data. So they also calibrate noise to privatize that query that is shown to be sensitivity 1. And then there is a gate that measures whether the distance at which you found the breaking point is too far off or too nearby. And based on the threshold, they decide whether you can release or cannot release with the proposed local sensitivity. So this is great. But what does it mean when we put in PTR in the face of in the context of neural networks? Because in there we don't know what the local sensitivity of a typically complicated neural network is, and so on and so forth. Okay, so that's one sort of a bottleneck when it comes to neural networks. So in this, now moving to the setting of inference within this context of not knowing the not knowing the sensitivity or the global sensitivity of a neural network, not knowing how to use PTR in correspondence to a neural network, and also moving to the inference regime where you're talking about data points x and x prime, like you see in the slide. In this setting, there's been so one thing we banged upon is this notion of metric DP that has come forth, because I said there's been different equivalents of DP and relaxation DP. One of them is metric DP, which generalizes instead of using the Hamming metric, which is traditionally the notion of neighborhood of two input points being neighboring, it generalizes a different metric of choice that one could use instead of the Hamming metric. And also it generalizes the metric with which you're comparing the output of your queries to be close by or not. So in this setting, there's the local sensitivity within a neighborhood, and there is then around a point. Then there's also, in function in analysis, there's this notion of Lipschitz constants and local Lipschitz constants around a neighborhood. Intuitively, these are kind of similar notions, and going beyond intuition, they are also connected. The local Lipschitz constant around the neighborhood happens to be an upper bound around the same point of the local sensitivity. Okay, so this is possibly a good start, or at least one start that we've exploited, because you don't know a good way to propose a local sensitivity to a neural network. But if there was a way to estimate the local Lipschitz constant of a neural network at a point around a neighborhood, then that could be a starting point, at least to the first step of the modified PTR algorithm in this setting. Okay, and computationally speaking, there indeed do happen to be the estimators for local Lipschitz constants for neural networks outside of our work, which we use as a black box or we exploit. And I've cited some of these papers by Jordan and Demarcus from URBS 20 and by Wang et al. In URBS 22. And there's this slew of works in that problem space in itself. And the one we've used in some of our experiments was called LipMIP. So it's like Lipschitz constant estimation using mixed integer programming, which is the Jordan DeMarcus work. But I believe there's an improvement in that space as well that I've not surveyed since we got published. Okay, so as long as you have this, that's a good starting point for exploring PTR. Secondly, there's this impossibility notion, because now you're talking of the inference problem as opposed to like the central DP problem where you have an entire data set and it's not the training of the weights, the training weights that you're releasing privacy, but you want to inference with privacy. So there's, firstly, that is not a problem that is possible to solve. This has been mapped to what is known as a impossibility of instance encoding. That's the impossibility problem. As it is, it's not possible to solve. And from an intuitive standpoint as well, this is not a statistic. There's infinite possible inputs. So any possible input would change by a Hamming of one, even if it is very, very different when you're talking of two XX primes. And that's the nature of the line that makes it hard to tame when you're talking of private inference as it is. That's hence we've been looking at relaxations, this scenario, right? So we've been looking at So the relaxation we looked at is based on metric DP in the local setting. So it's a local metric DP where you're generalizing first from the Hamming distance or notion of neighborhood to a generic metric. Could also be some sort of a L alpha, L beta metric, L1, L2 kind of metric. And then we also got inspired by the notions of group privacy, because typically, even in the local DP setting with Hamming distance, people have been looking at Hamming distance of one being the measure of when things are different. It could have been two, it could have been three. I mean, it could have been a different number, abstractly speaking. So such is the idea of group privacy. So we generalize the local metric DP with this kind of a neighborhood where there's a notion of R that you can choose as well as to what your neighborhood is. Okay, so that leads to this this notion of privacy, which is with the notion of R kind of a neighborhood. So your neighboring points with respect to choice of metric, you have this local metric DP, which is we call reconstruction privacy. This is one way of a relaxation as an antidote to get away from the instance encoding problem. Okay, these are some references to metric DP by Chatzico-Kolakis et al., and also to the instance encoding problem by Carlini et al., and so on and so forth. Okay, one good thing, because when we keep starting looking at equivalences and relaxations, comes a question of, is this an equivalence or is it a relaxation or is it like even like a stringent, even more stringent privacy? We need to understand a few things that hold and do not hold in comparison to the classical DP that people know protects from or what holds for classical DP. So one notion of, I need to remove this guy. Okay, that's been, okay, we'll adjust with that for this slide. Okay, there's been a notion of understanding or modeling a Bayesian attacker in the context of traditional DP, which is given that which is basically given that you conditionally provide the output of a so-called mechanism, which is differentially private, and the question is trying to bound whether the suspicion of the what is the probability of the suspicion of the attacker going to change by. So the attacker could have, since it's a Bayesian setting, could have a prior knowledge, which is maybe very weak or maybe very strong with respect to conducting a membership entrance attack. And then comes the question, conditioned on the attacker also getting an additional information of the output of your mechanism, if this conditional suspicion is also bounded, then that's another notion of DP, equivalent property of DP, I would say. So one good thing is when Chatzico-Kolakis introduced the metric DP, et al. Introduced the metric DP notion, they also proved that it also, for example, preserves this Bayesian, the prior becoming not too strong a posterior condition and observing the output of the mechanism. And that is also bounded. This notion of Bayesian attacker prevention happens in metric DP as well. So that property carries on into our framework too. Okay, so again, looking at the broader steps again, because we looked at the entire PTR steps for the traditional PTR, proposed test release. Now looking a bit at the broader steps of our extended PTR in this context of neighborhood reconstruction privacy with local metric DP, right? With a specific neighborhood R. So most steps are the same, except for things like you propose for you. Well, you choose a neighborhood, you propose a Lipschitz, you have a proposed local sensitivity that you propose, and you want to figure out the gate for lifting it or not. So in this, so that you can calibrate with noise, as you see in the last step, you unrelease your query if it was good enough, a local sensitivity proposal. But in our setting, in order to figure that out, we are using the local Lipschitz constant that we base on these computational methods to estimate these in an exact form, as opposed to an approximation. And then we try to do some sort of a binary search, like a golden section style search, in terms of our neighborhood. And then we try to figure out if the nearest breaking point passes the threshold of still being corresponding to a good proposed sensitivity or not. So it's this central part that changes a bit. The rest is the same, which is once you find the distance to the nearest breaking point, which is also happens to be a function of your sensitive data. So you also first privatize that query, which we show is a global sensitivity 1 query. And then once you privatize that, there's the standard gate that we use to whether result or not, to release or not release your query. So now zooming into this kind of aspect a little bit. And the reason we use, before we zoom in, I would say that the reason we use the local Lipschitz constant, just to recollect, like I said before, is this happens to be bound over your local sensitivity. So if you don't know where to start your local sensitivity from, this is at least one way to start it from. You start your proposal from. Okay. So finding the distance to the breaking point, right, in the context of neural networks. So finding the distance, so proposing is, well, what is computationally feasible or doable, practical was to estimate a proposed local sensitivity based on your local Lipschitz constant, estimate local Lipschitz constant. But then comes another question. If you were to find the distance to nearest breaking point, even within a neighborhood, there's many other points with which we need to compute the local sensitivities for in order to see if it surpasses the proposed local sensitivity so that you found a breaking point. But that again is not easy because now you have this complicated neural network and you need to be able to somehow optimize and figure out the local sensitivity in this continuous space. And we don't have a way to do that yet. I mean, if there was, this is an interesting question itself, if this could be posed as some sort of problem. But what we go about is do something more traditional, like try to, if we come up with a function which happens to be a lower bound to this quantity, which is the distance to the breaking point. And we also show that that lower bound happens to be also a global sensitivity 1 query, and hence we release our rule based on that to find the breaking point. So that's the zooming in, a bit of a zooming in of the steps. Yeah, so this might be a good time for some questions before I do a segue into some future work that we've been doing on the specifically the activation release problem as opposed to the inference data problem that we looked at. Or if you think we should do this in the end because it's being recorded, we could do the questions in the end as well. I'll wait for the organizer too.
If people have questions right now, we can take a short break for questions. But if if no one wants to come forward, I guess we can keep going. So, is there any question right now? I'm taking this as we don't have any question on the first part, so I think you can keep going for now, and then we'll have more at the end.
Great, sounds good. Yeah. This is easier because instead of me searching all the windows and getting lost in my own windows. So, all right. So now is a segue to a similar setting in terms of the problem, which is privacy for activations. Now we've discussed post hoc for inference. We want to understand mechanisms. This is a bit of a future work going forward for privacy for activations. Where does this usually show up? Certainly not in federated learning, because federated learning has been more about releasing weights of the neural network. So there's more like the traditional PPML problems people are looking at heavily. But this release of activations shows up in distributed ML paradigms in a variant of FL called split learning, which is a bit less popular, not as popular as federated learning, but it has its own benefits too. So in this variant of distributed ML, the entire neural network doesn't lie in the client like it does in the FL. The neural network is basically split. So your neural network is split at some intermediate layer. And in this setting, what is communicated in this paradigm is just the activations from the intermediate layer during the forward prop, and similarly, the gradients only belonging to the jump from the intermediate layer, not the entire gradients, to be sure, and not the entire activations either way. So this basically causes heavy gains in the size of your communication in utilization of your communication bandwidth, because the payload is much smaller in this mode of training. Of course, there's questions of how to synchronize. There are many different ways of doing split learning. This is not a split learning talk, but this is a setting where release of activations with privacy is a requirement. Although split learning, just like traditional FL by itself, is not formally private. It's a distributed machine learning or a data or a model parallel method for training. In this setting comes the question of privacy for activations, which is a bit of the sister question to privacy during inference that we looked at. Now we're in the training setting as opposed to inference setting, but for activations, which still has this problem of being one-to-one kind of a statistic in some sense, as opposed to one-to-one kind of a function as opposed to weights, which is an intra-statistic. So here we've been exploring this paradigm of power learning on the privacy aspect. Here, before we get to the formal nature of how the privacy is provided, there's some more finer details of how the training is conducted here, because this paradigm was designed as a bit of a co-design between the nature of training and also between the privacy mechanisms. So there's a bit of a co-design between distributed training and private learning. So I'm sharing the distributed aspects of the co-design first. So in this setting, the client, or the weak or resource hungry client, is basically going to keep a smaller surrogate model that it's going to train for gaining utility, but this is a much smaller model because it can't handle the large model in the server. At the same time, it has a privatization piece, which it needs to somehow formally privatize so that the activations released from the privacy network, when they learn in conjunction with the smaller surrogate utility network, have some sort of a privacy guarantees, so that those activations are sent to the server where there's a more major resource-based training that continues to complete the task. So this is the setting of co-design. There's some benefits from the distributed nature, because if this could be achieved, you have it's like you're learning a private embedding that you're releasing once for all. There is no back and forth synchronization or like multiple rounds. Of course, it comes at some cost of utility, but like in traditional practical deep learning, we are not providing any generalization theorems or guarantees in here. And the utility is what it is based on purely empirically squeezing out whatever utility squeeze out. What we provide is the nature of the guarantee is more in the formal nature of the privacy for the activations when you learn in this setting. Okay, so comes the question of how we privatize in this setting. So we base our idea based on some guiding principles of probability flows. So there's this classic change of variable theorems people have applied to probability density functions. So if one knew what is the PDF of an input random variable, upon applying a bunch of transformations, the change of variable theorem lets us know what's the PDF after the transformation. So what is the PDF of the output after given transformation if you were able to characterize the PDF of the input? And it depends on the Jacobian of your transformation. Okay, so this is taken from Gabriel Peer, from a tweet of his, because he's very popular at he has some very well-known tweets that visualize different phenomena. So there's a visualization of the change of variable theorem in univariate settings. So if you had a blue distribution, if you apply the exponential transformation, the change of variable theorem based on the formula results the PDF after the transformation, just output PDF. Similarly, this is a visualization of transforming from the uniform random variable, the grid, to 2D Gaussian contours, so like multivariate 2D case, using the change of variable theorem. Okay, so why are we talking about this? That's the question. So there's an equivalent notion of DP called Lipschitz privacy, which has connections to this. So the definition of Lipschitz privacy is as follows. If your log probability density of the outputs of your queries applied to neighboring data sets were bounded in this Lipschitz sense, then it's called, it's known to be epsilon Lipschitz private. There's an equivalent and more practical or computationally wieldy notion of this under some assumptions, under some mild assumptions, which results in this equivalent definition. If your norm of the gradient with respect to your sensitive input of the log probability of your output of your mechanism is bounded up to an epsilon. This is called epsilon Lipschitz private. Now, what is the equivalence with DP? If your data is coming from domains where the max separation between any two data points is known in that domain to be, say, alpha separated, so no data point is more separated than alpha, no pair of data points is more separated than alpha. And then if you, on that domain, if you have a mechanism that results in an epsilon Lipschitz privacy guarantee, then that is equivalent to alpha times epsilon differential privacy guarantee. That's the equivalence of translating from here to the other one, the definition. Okay. Now, of course, the question is, well, in the context of the talk, the question is, how do you utilize this in the context of neural networks? Because that's not a traditional transformation like applying an exponential or something of that sort. So this is the last function that we proposed by so the proof strategy is by superimposing the notion of Lipschitz privacy and also utilizing the change of variable theorem, because the change of variable theorem takes you into the PDF space of objects, and then when you constrain that to satisfy this definition, we came up with this privacy loss term, the first term, which is equivalent to so bounding this term is equivalent to gaining Lipschitz privacy. And in terms of learning a process, in the context of learning, because just by itself you might get trivial answers or extreme answers which may not be of any use, but when you regularize this privacy loss with a utility loss purely for learning, then you have some sort of a game going on in terms of hopefully squeezing out activations that maintain the Lipschitz privacy while satisfying some utility. But let me comment on a few things on this, because there are some aspects of this which are empirical. There are some aspects which are always formal. So it's important to comment on the delineation here. Say you, and there's no exact epsilon you see here, because this is a loss function that you're seeing. So say a user in this setting has aimed for a given specific epsilon 1 of Lipschitz privacy that he wants before he releases his activations after the transformation of the neural network. And now comes the game of trying to optimize the neural network and see if your loss function for the privacy loss term goes below that epsilon or not, below that epsilon 1 or not. If it does, well and good, you can release all your activations. If not even a single activation goes below that, you cannot release anything. But you could also be in a setting where you see some activations meet this mark and some do not. And then now you get this option of doing some sort of a few-shot learning or private release for learning, where you can only know which are those activations you're good to go to release because they meet the Lipschitz privacy bound. So that's the overall criteria. And since we're talking of, I think, PyTorch and TensorFlow in the context of neural networks, what you see is not what you exactly see, right? So it's not the reality. So you're just computing a statistic. So minimizing this loss doesn't mean it's exactly Lipschitz private. And neural networks are complicated loss functions by themselves. So we do some sort of a calibration and uncertainty calibration around it so that we can guarantee that because this Lipschitz privacy term, the cost term that we propose also depends on some intrinsic nature of the distribution of your data that has nothing to do with the transformation of the Jacobian, which is this first term. This is like the density derivative and the densities. So we plug in confidence intervals and density estimates, and we take the more conservative setup and recalibrate when we have an observed epsilon, what is the uppermost bound of epsilon prime that you can release in a probabilistic way so that your delta gets eaten up as well by a larger delta. And then you have this calibrated reported epsilon. The effective epsilon is different from the observed epsilon. So this is a visualization, for example, of the histogram of our Lipschitz losses, Lipschitz privacy losses. So say based on this histogram, if someone was shooting for a privacy level of 1 or below, epsilon level of 1 or below, and this basically is saying you can only release the activations on this left side of the tail and not release any of these because these other samples are coming up with activations which do not meet that bound. They're not contracting enough or stable enough to cause Lipschitz privacy. So this is a way to characterize an intrinsic cost of privatization or some sort of a per sample attribution of hardness of privatization for a given pipeline. So if you had a neural network pipeline, you will be this method allows you to attribute which are the samples that are easier to privatize and which are not, and you have this number, which is this privacy loss. Okay, in terms of some initial experiments, because what's been very traditional, if you put DPFTRL and the wonderful things we've been listening in the PPML community, but if you go back to the traditional baseline of DPSGD, without doing many major engineering tricks or tuning, we are able to meet similar performance through this power learning paradigm from a utility privacy perspective. But what is the benefit in that case? The benefits are these side things that you're getting, which are still substantial, which is since we co-designed our setup of distributed ML with respect to the private ML aspect, we have this tremendous gain in communication because you only do one-shot embedding release, and you're also allowing for use cases where you need to release activations as opposed to weights of trained neural networks. That's one benefit. The other benefit is the second order takeaways of attributing privacy costs of hardness of privatization per sample, and also trying to figure out which samples can be used for few shot learning while still preserving privacy. So these are the other side benefits that we get. Okay, I think that's a good point to close the talk, and this is a bit of a slide that I've used to inspire myself. I'm not sure how useful it will be, but I always try to recollect it towards the end of my privacy talks, which is
It's
formal
very
privacy is a
scary.
rich, yeah. So formal privacy is a rich field, and there are many other rich fields around it, and there's amazing researchers in all of these areas. But there's also, it's good to bring up the fact that there are some very interesting questions at the intersection of privacy and these other fields, right? So, but that's what it is. That's, I guess, a bit of a spiel, but that's it. So acknowledgements to some of the researchers that were involved in some of these discussions and relevant works. Yeah, cool.
Oh, thanks so much for the great talk.
Yeah,
Can I actually start by asking just like a potentially very stupid technical question? Can you go back to the Lipschitz privacy definition that you had on the second part
yeah.
of the talk?
Okay, yeah,
Second
yeah.
one?
It's gonna come here.
I just want to start it again for a second.
Maybe this one. Yeah.
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 Okay. So if I take the distance function to be the number of entries that differ between you and U prime by group privacy, that's exactly differential privacy, right?
Yeah. Yes. The only difference is you're in the log density scale here.
Right, that's right. But like this is saying that the ratio of the probability in mu and u
Yes.
prime is bounded by exponential of epsilon of the distance. If I actually just plug the distance to be the number of different entries, then that is
Correct.
exactly differential privacy. I see. So
That's
differential
correct.
privacy is like a special case of that definition.
Exactly. And actually, the
Okay,
paper
that
that
makes sense.
introduced Lipschitz privacy directly connects it to DP to the Laplace mechanism. It says Laplace mechanism is optimal, universally optimal for the queries that it deals with when looked at the angle of Lipschitz privacy as well. Yeah, the paper is literally titled the optimality of the Laplace mechanism. It's not even titled Lipschitz privacy, and hence it's less heard about, although they again show an exact equivalence to DP. Yeah. Yeah. Unlike say like Rendy DP or zero constant DP, which are like very fancy these days, and people use them and hear about them a lot.
Yeah, does anyone else have any questions? All right, I'm guessing like if there is no other question, we can thank Praneeth again for a great talk. Yeah, thank you.
Great, thank you. Yeah, thank you for letting me speak.